Welcome to Cambridge IGCSE Physics, Lesson 39.1, Energy Transfer in Circuits. Today we explore how electrical circuits transfer energy from sources to components and how this energy transforms into useful forms or dissipates to surroundings. This fundamental concept underpins all electrical systems in our modern world. Let's examine our learning objectives for today. By the end of this lesson, you'll be able to, first, understand that circuits transfer energy from source to components. This means recognizing that batteries or power supplies provide energy that flows through circuits. Second, no energy is transferred to surroundings as heat. All electrical components dissipate some energy as thermal energy. Third, identify energy transformations in electrical devices. Different components convert electrical energy into light, sound, motion, or heat. These objectives align with Assessment Objective 1, which tests your knowledge and understanding of fundamental physics concepts. Now let's define our key vocabulary. Each term is essential for understanding this lesson. First, energy transfer, which means the movement of energy from one place to another. In circuits, this is electrical energy moving from source to components. Second, circuit energy, which means electrical energy flowing through conducting paths like wires and components. This energy can be measured and calculated. Third, source, which means a device providing electrical energy, such as a battery or generator. The source creates the potential difference that drives current. Understanding these terms precisely is crucial. Remember to use SI units, joules for energy measurements, and watts for power calculations. Let's explore our first core concept, energy flow in circuits. The fundamental principle states that energy flows from source through circuit to components. This means electrical energy originates at the source, such as a battery, travels through conducting wires, and transforms in components like lamps or motors. The definition is, electrical energy originates at source, travels through conductors, and transforms in components. Each component receives energy and converts it to other forms. Mathematically, we express energy as E equals P times T, where E represents energy measured in joules, P represents power measured in watts, and T represents time measured in seconds. The circuit diagram illustrates this flow. Energy starts at the source, flows through the circuit, and reaches each component. Notice how the arrow shows energy direction. This principle is fundamental because it explains how all electrical devices receive and use energy. Now we examine the experimental method for measuring energy transfer. This follows Cambridge IGCSE standards. The standard procedure involves measuring power and calculating energy transfer. The apparatus needed includes an ammeter to measure current in amperes, a voltmeter to measure potential difference in volts, a stopwatch to measure time in seconds, and a variable resistor to control current. The method consists of these steps. First, connect the ammeter in series and voltmeter in parallel. Second, record current and voltage readings simultaneously. Third, calculate power using P equals V times 1. Fourth, multiply power by time to find energy transferred. Safety is paramount. Use low voltage supplies under 12 volts. Check all connections before switching on. Avoid short circuits which can damage equipment. The calculation sequence is power equals voltage times current, then energy equals power times time. Let's work through our first example. The problem states, a 12-volt lamp draws 2 amperes current for 5 minutes. Calculate energy transferred. We are given voltage equals 12 volts, current equals 2 amperes, and time equals 5 minutes, which converts to 300 seconds. We need to find energy transferred in joules. Step 1. Write the equations. We use P equals V times Y for power, and E equals P times T for energy, where P is power in watts, V is voltage in volts, I is current in amperes, E is energy in joules, and T is time in seconds. Step 2. Calculate power. P equals 12 volts times 2 amperes equals 24 watts. Step 3. Calculate energy. E equals 24 watts times 300 seconds equals 7,200 joules. Step 4. State the answer. The energy transferred is 7.2 kilojoules to two significant figures. Example 2 analyzes energy transformation in an electric motor. The problem is, an electric motor has 100 watts input power and 75 watts mechanical output power. The data shows input power of 100 watts and useful output of 75 watts. Now we analyze energy flow. First, calculate wasted power. Input minus output equals 100 watts minus 75 watts equals 25 watts wasted. Second, find efficiency. Efficiency equals useful output divided by total input times 100%. This gives 75 divided by 100 times 100% equals 75% efficient. Third, identify energy to heat. 25 watts converts to heat energy every second. Fourth, identify the transformation. Electrical energy transforms into mechanical energy plus heat energy. The diagram shows this energy flow. 100 watts electrical input splits into 75 watts mechanical output and 25 watts heat loss. Mathematical skills are crucial in physics energy calculations. Let's examine 3 key skills. First, equation rearrangement. When we need to find a different variable, we rearrange algebraically. Starting with E equals P times T, where E is energy in joules, P is power in watts, and T is time in seconds. To find power, we divide both sides by T, giving P equals E divided by T. To find time, we divide both sides by P, giving T equals E divided by P. Second, unit conversion. To convert minutes to seconds, multiply by 60. To convert kilojoules to joules, multiply by 1000. These conversions ensure consistent SI units. Third, efficiency calculation. Efficiency equals useful output divided by total input multiplied by 100%. This quantifies how effectively energy transforms from input to useful output, with the remainder becoming waste heat. Now practice what you've learned with these 3 questions. Question 1 is basic level. It asks, a 6-volt bulb draws 0.5 amperes current. Calculate power consumed. Use P equals V times 1. Question 2 is intermediate level. It states, a heater uses 2 kilowatts for 30 minutes. Find energy transferred in megajoules. This requires unit conversion and the energy equation. Question 3 is advanced level. The question is, a motor has 500 watts input and is 80% efficient. Calculate heat produced per minute. This tests efficiency concepts and energy transformation analysis. For all questions, remember to show you're working clearly. Include units in every step and check your answers make physical sense. Write your answers now, before looking at the solutions. Physics principles power our modern world. Let's see how today's energy transfer concepts apply in practice. In technology, smartphone batteries demonstrate energy transfer perfectly. Chemical energy in batteries converts to electrical energy, which transfers through circuits to power processors, illuminate screens, and drive speakers. Each component transforms electrical energy into its specific function. In scientific research, solar panels showcase energy conversion. Photovoltaic cells convert light energy directly into electrical energy, demonstrating renewable energy transfer principles. In engineering, electric vehicles optimize energy transfer for maximum efficiency. Engineers design circuits and motors to minimize energy loss as heat, maximizing useful mechanical output. These applications show why understanding energy transfer matters. Career-wise, this knowledge leads to electrical engineering designing power systems, renewable energy developing sustainable technologies, and electronics design creating efficient devices. Let's review the solutions. For question 1, power equals voltage times current. P equals 6 volts times 0.5 amperes equals 3 watts. This is reasonable for a small bulb. For question 2, first convert time. 30 minutes equals 1800 seconds. Then E equals P times T equals 2000 watts times 1800 seconds equals 3.6 million joules, which is 3.6 megajoules. For question 3, 80% efficiency means useful output is 400 watts. Wasted power is 100 watts, which becomes heat. Per minute, this equals 6 kilojoules of heat energy. Now, exam success tips. First, always show you're working step by step. Even if the final answer is wrong, you earn marks for correct method. Second, include units in every calculation step. This prevents unit errors and shows understanding. Third, check if your answer is reasonable. If you calculate gigawatts for a household appliance, reconsider. Fourth, read questions carefully. Command words tell you what to do. Calculate means find numerical answer. Describe means state features. Explain means give scientific reasons. Let's summarize today's lesson on energy transfer in circuits. The key points to remember are, first, energy flow. Circuits transfer energy systematically from source to components. Energy originates at batteries or power supplies, travels through conducting wires, and transforms in components like lamps, motors, or heaters. This flow follows conservation of energy principles. Second, energy transformations. Electrical energy converts into many useful forms: light in bulbs, heat in resistors, sound in speakers, and motion in motors. Understanding these transformations helps analyze circuit behavior. Third, efficiency concepts. Not all input energy becomes useful output. Some energy always converts to heat, representing energy loss. Calculating efficiency helps evaluate device performance. For further study, review energy equations, especially E equals P times T and P equals V times 1. Practice unit conversions between joules, kilojoules, and megajoules. Master efficiency calculations using the ratio of useful output to total input. The next lesson covers electrical power in detail, building on today's energy concepts by exploring power relationships and practical applications.